To this machine course, and we are now doing a very important thing, that is we are really now going towards 3-phase induction motor, and the groundwork for that we have already done rather in detail, including the windings of a 3-phase winding and so on. So, recall that the interesting part of a rotating field created by a balanced 3-phase current is this, that the windings are stationary, but if the windings are excited by 3-phase supply, it will produce a rotating magnetic field, and this is the thing we should always keep in mind. And suppose this is R 1, this is Y 1 and this is B 1, which are mutually apart, and if you connect it to supply R s, supply Y s and supply B s, this is supply S U P, supply R Y B. Then the result is that a rotating magnetic field, and this sequence, supply sequence is R Y B, supply sequence. Then what happens is this, a rotating magnetic field will be developed, whose peak value will be 3 by 2 B max. Okay. This is the peak value, and it will rotate in this case this way, because from leading to lagging phase it rotates, okay, 3 by 2 B max. If the same thing, same machine, if you do it like this, suppose the winding I am not disturbing, whatever it is there, it was marked R 1, Y 1, B 1. But what you have done is this, R supply you have connected like the previous one, but this Y supply you have connected to the B of this Y supply, and B supply you have connected it here, and then also a rotating magnetic field will be developed, whose strength will be 3 by 2 B max, and this one will rotate this way, and it will be rotating with respect to the coils, with respect to the structure which houses the coil. Now, what is the value of this speed? The value of this speed is 2 f by p, so much of RPS, and its speed also is 2 f by p, so much of RPS, and these are mechanical speed, this speed we commonly understand. So, this is the thing. Of course, the electrical speed is always f RPS. What is f? F is the supply frequency, So, by interchanging two supply terminals, the rotating field, direction of rotation of the field may be reversed if we wish. So, this is how things are done, and this speed is written N s, because it depends upon supply frequency, which is constant and is called synchronous speed. So, N s is the speed of the field, is called synchronous speed. Clear? Okay, one interesting thing, and what is this B max? Remember, if I max is the phase maximum current, because sinusoidal current they will draw phase maximum current corresponding to that I max whatever is B max, that is B max, that you should remember. Achha, now one important thing I will tell, which is important in the sense that it suppose I tell you right at this time it is rotating after all. In one of the case you consider, suppose this one it is rotating. Right now, where is that resultant field? Okay, I cannot see that resultant field, nothing. But about one thing I am pretty sure, that is what I am trying to tell. What is that thing? If right at this point of time, these currents I can see in the oscilloscope, if the R phase current is maximum value I max, then I am sure the resultant field will be along the x axis. That is what I want to tell. Similarly, when the y phase current will be maximum at whatever time, at that time you can be pretty sure that your resultant field of strength 3 by 2 B max will be along y phase axis and so on. At least about those 3 points I can say, about those 3 instants. At whatever instant, if we find R phase current is maximum, resultant field will be horizontal. Otherwise, if y phase current is maximum, it will be like this and it will be like that. But in any case, it is rotating. Now, imagine that this winding is lying on a stator structure like this. There were slots. I will not symbolically I am drawing. It is like this, and this is stator iron. This is stator, and it houses 3 phase balanced winding like this, and from these 3 terminals come out, that we are calling R1, Y1, B1 machine terminals, and to which I have connected this supply. This supply was connected here, and the result is a rotating magnetic field, a field pattern, okay, and that is moving. So, simple way to show it by a line and moving either this way, suppose phase sequence is RYB, it is moving like this. And it is moving with respect to whom? With respect to the structure, that is stator. Stator does not move, it is well grouted to the ground, it is not allowed to move. Therefore, with respect to that stator structure, therefore, with respect to anything which is not moving, so I can pretty well say with respect to a stationary observer also. Stator and stationary observer are one and the same thing. So, it will be moving like this. Then if it is a magnetic field moving, a sinusoidal magnetic field, then we discussed about one very interesting problem, that is, suppose on the rotor of the machine, I have a coil which may be also distributed, suppose single phase coil like this distributed. This is on the rotor. As this fellow moves and suppose rotor is not allowed to move, it is held by hand, then across the 2 terminals of the rotor there will be induced voltage produced. In general case, this is the rotating field, speed is ns, and suppose also rotor is moving nr by suppose some external agency, he is also running this fellow, mechanical speed nr, ns nr are mechanical speed suppose, and rotor is also allowed to move. In that case, there will be a voltage induced in the rotor coil. How much will be that voltage? That voltage will be root 2 pi frequency. Frequency will be decided by the relative speed ns minus nr. by 2 if it is rotating in the same direction, nr is less than ns suppose. So, it will be this, then flux per pole. How to calculate flux per pole? Okay, 3 by 2 B max, it is some sinusoidal like this is 3 by 2 B max. So, 4 by P, that 3 by 2 B max Lr will be the flux per pole. This is the relative speed between these two into the effective number of turns of these distributed coils, which will be kW into N2. Suppose N2 is the number of turns, total number of turns. Physical number of turns is N2, it gets reduced by a factor of winding factor. We know how to calculate kW, which is nothing but kd into kp. Okay. So, this will be the expression of the induced voltage across this coil, RMS value of the voltage. This will be the induced voltage. Ns, Nr are in mechanical RPS, that is why I have to multiply it by P by 2, and the frequency of E2 will be equal to P by 2 Ns minus Nr. Frequency of E2, that is say F2 is equal to P by 2 Ns minus Nr. So, frequency of the voltage will be this one. Therefore, we see that your supply frequency was F, but the frequency of the induced voltage in this coil will be P by 2 Ns minus Nr. If Nr happens to be 0, that is suppose you do not allow the rotor to rotate, then of course, this will be F2 will be equal to supply frequency F if Nr equal to 0, that is true, but if it is not, then the frequency of the induced voltage here will be 0. See, we have looked at transformer, you energize the primary winding with frequency F, the induced voltage in the secondary will be of same frequency, but here if you regard the stator coils to be your primary where you are connecting supply and rotor coils to be your secondary, we immediately notice that if rotor rotates, then the frequency of rotor voltages and applied voltage on the stator, these two will be different. In fact, the rotor frequency will be reduced by a factor of Ns minus Nr will decide what will be the frequency of the rotor induced voltage. So, this is the basic idea that we will further build up, but I hope this point should be absolutely clear what we are doing. And also it should be noted, therefore, I can now draw this diagram in a much more straightforward manner. Symbolically I will draw. Okay, this is your stator, and because I have now understood what is going on, so I will draw the stator coils like this. I will connect it to the supply, and in the rotor I have a coil. I will just show it like this, rotor coils, and it is rotor. I will indicate by putting a circle around it, and rotor is moving something like that with a speed say Nr, and stator field, which I will just call Bs, which is the strength of peak value of this one is 3 by 2 B max. So, Bs, suppose let us also simplify that, I will write it like this, and it is suppose rotating in this direction with mechanical speed, mechanical is equal to 2 F by P, so much RPS. Multiply by 60, you will get RPM. So, we will just simply draw like this, and then I was telling what will be the induced voltage here when n are equal to 0. Obviously, you can easily see if suppose it so happens you are driving the rotor such that n are equal to n s, then no relative speed exists between the coil and the field. So, induced voltage is to be 0, that is what is taken care of by this term, E 2 will be 0. However, the moment there is a relative speed existing between the field and the field which is moving and the rotor, which is also driven as I have told you by some external agency, there will be bound to be some induced voltage in this one. Okay. Now, the second thing what I am telling you, listen carefully, that is, suppose in this rotor, at least let me draw, this is suppose stator. And this is stator iron, and what I told, there are coils or coil sides in each slots, you know. I am drawing totally wrong, it should be here, is not? These are slots. In these slots the conductors are there, the inner surface, this is slot, this is slot. This is slot, and here you place the conductor, slot, here you place, like that 3-phase balanced winding is there on the stator. Now, similarly on the and 3-phase winding, 3-phase. Similarly on the rotor, which is separated from the stator by the air gap Lg, etc. Rotor too will have suppose slots and teeth, and there also suppose these are the slots, I have placed rotor conductors, which is also a 3-phase coil. So, this is rotor and 3-phase winding is also wound on the rotor, 3-phase winding. So, instead of a single coil on the rotor, I will now have a balanced 3-phase winding also on the rotor, just similar to that of stator. And such a scenario can be simplified in its representation in this way. I will draw it like this. Okay, this is my stator R 1, Y 1 and B 1. Suppose rotor, this is stator, stator coil. This part is stator, and rotor part also it is a 3-phase distributed coil. So, this can be also represented as some R phase, Y phase and B phase, and suppose this rotor terminals, this let me call RR, this is YR and this is BR, like this. So, this is the rotor 3-phase winding, which is also balanced and 3-phase type. So, so this is the rotor part, and it can be rotated externally or maybe it will rotate on its own when you energize the stator, we will see that. But the point is that the and suppose the rotor terminals are kept open circuited, what is going to happen? With rotor terminals open circuited and stator supplies from supply RS, supply BS and supply YS, we know a rotating magnetic field will result, which will be like this Bs, and it will move in this direction provided phase sequence is r by b. It will move with a speed ns, and now it will move in this direction, so that instead of a single coil as in the previous example, we have 3 coils which are separated by 120 degree electrical apart. Therefore, if each coil will become a seat of EMF, and since it is balanced winding, number of turns of the secondary coils are suppose N2, N2, N2 per phase, then there will be induced voltage in this coil, in this coil, in this coil, and RMS values is expected to remain same. Why it should change? Only thing what will change is that whatever is happening now to the R phase coil is going to happen to the Y phase after 120 degree, because maximum flux linkage occurs with R phase when the field is here, and that maximum flux linkage will occur to B phase when this B s I am showing, it will be here. So, the phase difference of the induced voltage in the Y phase will be lagging by 120 degree. Similarly, the induced voltage in B phase will be maximum after 120 degree, Y phase has got the maximum value. So, there will be once again balanced 3 phase voltage induced in each of the coil, and suppose the rotor speed is 0, because it is open circuited and there is no prime mover connected, nothing. You have simply energized this will be the thing. Acha, let us not forget another thing, that as this rotating field moves, it is moving with respect to whom? Always right, with respect to stator, this NS is, and you are sitting in the R phase. You immediately see that as this field moves in this R phase coil, there will be induced voltage because of Bs. Similarly, there will be induced voltage on the stator Y phase and stator B phase, as there are induced voltages in RR, YR and BR in the rotor phases. Similarly, why not there will be induced voltage in this coil. And what will be the magnitude of that induced voltage? Suppose I say the voltage induced per phase in the stator coils RMS value is E1, it should be root 2 pi P ns by 2, because stator is of course always stationary. So, relative speed between the coil and the field is ns. So, P ns by 2, flux per pole, and winding factor of the stator into N1. What is N1? N1 is the number of turns of this, Nr equal to 0, and this is nothing but root 2 pi P ns by 2 is nothing but supply frequency f. So, it can be written as root 2 pi f phi kW 1 N 1. And what is phi? Phi is the flux per pole of B s. B s, if it is I am drawing like this, do not forget this B s maximum, B s maximum is nothing but 3 by 2 B maximum. This you should never forget. What is B max? When that phase carries I max current, whatever is B max. So, I can calculate the flux per pole, what is the area, this, that, 4 by P, etc. So, this is E1. Similarly, E2 per phase voltage in the RMS value of the per phase voltage will be root 2 pi p, since n r equal to 0, p n s by 2, same flux per pole, it has not changed, into k w 2 into n 2. What is k w 1? K w 1 is the winding factor of the stator windings, and k w 2 is the winding factor of the rotor winding. Therefore, when n r equal to 0, when n r equal to 0, you can easily see that E 2 by E 1 will be equal to k w 2 n 2 by k w 1 n 1, almost like a transformer. It was n 2 by n 1, but it is now. So, this k w into n 2 is called effective rotor turns per phase, effective rotor turns divided by effective stator turns per phase, here also per phase. So, it is almost like a transformer. What is the frequency supplied? F. What is the frequency of this secondary coil? F. So, it is almost like a transformer. Why almost? It is a transformer. It looks like you can step up or step down the voltages having same frequency. But only problem is I do not know yet what is going to happen if the secondary winding also starts carrying current, whether it will remain same in its operation like a transformer or it may differ. Earlier what people used to do, there was one machine called, that is the rotor of such setup with a stator winding and rotor winding, and it is not used as a motor, but what it does is you can move this by hand where the angles will be calibrated and lock the rotor, so that it does not move. Understood? It will be, it is not allowed to move, and if it is not allowed to move, I am pretty sure that the stator frequency, supply frequency and rotor frequency has to be same, because NR, in any case I am forcing the rotor also to remain stationary by locking it mechanically. In that case, what you can do is this, suppose the idea is very simple. This is your stator coils and rotor can be moved by hand before you energize it. Suppose I could place the rotor in this way, RR is here, YR is here and BR is here. That is, I align the stator R phase and rotor R phase, stator Y phase and rotor Y phase and rotor B phase like that. Then I energize these three with a balanced 3 phase supply and the rotor is not allowed to move. In that case, what will happen? This induced voltages will, that is the R phase voltage applied here and R phase voltages obtained here in the, if you love to call it secondary, they will be in phase. In transformer it is always stator applied voltage per phase and corresponding rotor induced voltage per phase, they are in phase, time phase. But here, since I have this provision, I can move this rotor by hand and then lock it. So, in one position I do it like this. So, this E2 and E1 they will be in phase. However, if I make this is suppose stator R1, Y1, B1 and rotor I will move it suppose in this position I keep it. So, rotor is moved and then locked, it is not allowed to move, that is what I will always maintain. It will be something like this, this is RR, this is YR and this is BR. Okay. Rotor not allowed to move, rotor is locked mechanically. And you energize this with a 3-phase supply as usual, this. Result is a rotating magnetic field PS, it moves in this direction, sequence is RYB and then it will induce voltage. Obviously, you can see the R phase induced voltage here E1 and R phase induced voltage here in the rotor. This voltage will lag this voltage by this angle theta, is not? Theta is the angle by which you have shifted. Therefore, with this arrangement, if you say this is called a phase shifter. Suppose there is a input 3-phase voltage, for some reason or other you want to get once again balanced 3-phase voltage and phase shift it with respect to the actual supply voltage by say 30 degree or by say 90 degree, whatever you want, you give this shift. There is calibrated dial, it will be there, you shift it, physically you are rotating it and initially the manufacturer will say, because after all from outside I can neither can see R phase of the stator not the R phase of this rotor, they will calibrate it. In fact, it can be done easily even if it is not marked, whether I have aligned, I will see where these two voltages are in phase, then I will say okay, R phase and this R phase are coinciding, otherwise not. So, that way you calibrate. So, it is called a phase shifter. This was used like this phase shifter, you can get a desired phase shifter. And also not only that, if you choose N1 N2 differently, you can not only have a phase shift of this voltage, but also a level change of voltage like a transformer. In a transformer, say single phase transformer, each phase winding voltages are in time phase, but here it is not. You can phase shift that input voltage by whatever angle you desire, and also the magnitude can be manipulated if you manipulate N1 and N2 if it is so necessary. But in any case, this is not designed for rotations, you lock it. Of course, we are not sure whether if this lock is removed, whether this fellow will start rotating or not, that is also we have not yet learned. In fact, he will show that if current flows in the rotor windings, because after all this phase shifted voltage will be connected to some load, no, these windings will carry current and it will have it must produce its own field and these two fields may interact and give you torque. But let that torque be developed, but I will also force the rotor not to rotate, that is what the whole idea is. There will be mechanical stresses by which you are locking this rotor. Because of this torque produced, hopefully it will produce a torque. So, whenever balanced 3 phase current will be flowing, when it will be flowing? When you load it. For some purpose you have changed the level of voltage and phase shifted with respect to the supply voltage, then it is to be connected to some load. The moment you connect load like a transformer, secondary you are loading, currents will be flowing and balanced 3 phase load you have connected, let us hope balanced 3 phase current will flow, and the moment it carries balanced 3 phase current, oh, very nice things happens, then this fellow too will produce a rotating magnetic field, and this we will discuss in my next lecture. Thank you.